What up, math friends? We're still out here on Orcas Island, and today we're going to be talking about Heisenberg Lie algebra modules. Wait, didn't you already talk about Heisenberg Lie algebra modules like a year ago? Yeah, totally. This is a review, and we're covering details that'll be important when we study Chapter 4 of FLM, which is to say, untwisted vertex operators and their algebra. The main theorem in the study of these objects is the Stone-von Neumann theorem. The Stone-von Neumann theorem, as you might recall, is kind of like a theorem heavily based in functional analysis, and we will not be doing any functional analysis, at least today. So we'll be not even reviewing the algebraic version, which we covered in a previous lecture, but we're just going to review some more fun facts about Heisenberg Lie algebra modules. Firstly, let's motivate our discussion from last time. You remember we talked about Heisenberg algebras, and the standard example, the prototype example, is the ladder operators associated to the quantum harmonic oscillator. So that algebra is simple. It has 3 dimensions. Those dimensions are spanned by a dagger, and 1, and the commutator of a with a dagger is equal to 1. Right? Whatever. So, but those are the operators associated to a quantum mechanics model for a spring. And what's fun about that is the set of physical states of that space is given by, obviously, a module for those operators. And that module can be represented as, like we physicists call it a Fock space. There's a vacuum vector, and then we hit it arbitrarily many times with a dagger. And in some sense, this set of physical states is therefore in a bijection with the natural numbers. Right? So they're called ladder operators because the operator A, acts on the vacuum, the state where nothing's happening, and annihilates it, sends it to 0. Whereas a dagger brings you off the ladder. So in other words, it takes you from the nth state to the nth plus 1 state, which corresponds to n quanta of vibrational modes of the spring. And then A itself takes you down to the vacuum, which is 0, and after that it goes away. So that's kind of the basic idea, the basic structure. But let's review some fun facts about Heisenberg modules. This isn't really a fun fact, it's more of a rule. We're going to be discussing a specific subset of Heisenberg modules, and those are going to be given by 2 conditions. Collectively, some people call them the vacuum conditions. The first is that the central element acts on the Heisenberg module as a complex scalar. That's it. Okay, good. The second condition is that there is a subspace of homogeneous degree that is maximal. In the following sense, let the module have a grading, an integer grading, then there is some number n for which any subspace of homogeneous degree greater than n is equal to 0. That is to say, it's trivial. From those 2 conditions, you can derive the fact, and we have in the past, that, so I feel like this is fun fact number 1, but we won't prove it, any such Heisenberg module that satisfies those conditions has a vacuum vector. And a vacuum vector is any vector that satisfies the following. All elements from, remember our kind of decomposition, H0, H plus, H minus, all elements from H plus annihilate that state. That is to say, map it to 0. That is to say, they're in the kernel of those operators. Then the algebraic analog of the Stone-von Neumann theorem that FLM proved in their text and that we discussed in a previous video simply observes the fact, well, it does a lot actually, lets us represent the irreducible Heisenberg module associated to a Heisenberg algebra H as the symmetric algebra over the abelian subalgebra of negative homogeneous dimension, that's to say H minus. So you see how this maps to the quantum harmonic oscillator problem, right? Basically all the A's live in H plus and all the A daggers live in H minus. So we can consider arbitrary polynomials in H minus, and that will define all of the operators that act on states that give us non-trivial values back. So in other words, that was fun fact about Heisenberg modules number 2. The irreducible Heisenberg module associated to a Heisenberg algebra H is the symmetric algebra over H minus. Therefore, any Heisenberg algebra that satisfies the vacuum conditions can be represented as a direct sum of copies of this irreducible representation. one copy for each dimension of the vacuum, which is the span of the vacuum vectors. So for the particular case of quantum field theory, right, where we're we're out of focus. Come on, focus up. So for the particular case of quantum field theory, where again, we're looking at maps from space-time, say R1, 3, to the reals, so for a real scalar field, or to whatever. Typically the thing to do is we Fourier transform that map, look at the Fourier modes. The operators of the algebra correspond to the coefficients in front of the Fourier modes. They are graded by a vector in R3, the spatial dimensions, and that vector is associated to a wave vector, the momentum vector of an excitation of the field, if you like. Or at least that's the case for non-interacting quantum field theories. And so in direct analogy with the harmonic oscillator, right, the space of quantum states for this field, this non-interacting scalar field, is just given by basically arbitrarily many polynomials in these A daggers, that is to say, half of the Fourier modes. These correspond to 1 particle states, 2 particle states, 3 particle states, however many operators you have. So specifically for the case of, let's say, choose a wave vector k, so A dagger k acting on the vacuum gives us a state, a 1 particle state, where the particle has momentum k, or h bar k, where h bar is that quantum mechanics constant, Planck's constant, divided by 2 pi that we normally set to 1 by choosing correct units. Now notice what I said there. Non-interacting quantum field theories. There's a whole story about different pictures in quantum field theory and different pictures in physics. And the interaction picture is one where basically you excise a compact subset of the space that you're interested in, Minkowski space, say R1, 3, and then you let your quantum field theory be defined on that compact subspace, and then you kind of find a way to link it together with an asymptotic version, and the asymptotic version is always free particles. And the reason for this is we know what the quantum states of free particles are. They're given by these modules of Heisenberg algebras. Once we allow the fields to interact, nonlinearities pop up and things get messy. And so what we lose is this correspondence, this direct correspondence between operators, that is to say, Fourier modes of the quantum field, and states of the theory. We no longer have that connection. And what is so fascinating about string theory and about conformal field theory in general is that whenever we have a conformally invariant quantum field theory, we end up with a bijection between the set of operators and the set of states. Even if it's interacting, even if it's nonlinear, even if it's crazy, even if it's in more than 2 dimensions, as long as it's conformal, we have that bijection. Sort of. For the case of 2 dimensions, right, Greg Moore and Natty Seiberg showed that you need 2 things. First, you need to show that you have conformal invariance for the theory defined on the sphere. And the second thing you need to show is you have modular invariance for the theory defined on the torus. And then from that's sufficient. Those 2 conditions are sufficient to define a quantum field theory with a state operator state correspondence for any Riemann surface, that is to say any 2-dimensional complex manifold, or any 1 complex dimensional manifold, period, which would be basically any string world sheet that you'd want to consider. So that's cool. Extending that to higher dimensions is not easy. Jan de Boer and friends wrote a paper a while back trying to do that. I'll link it in the show notes. It's, like I said, it's not easy. Now, if you're a physicist in here being like, what the heck are you talking about? I would encourage you to think a little bit about defining quantum field theories. Normally we just kind of do it the way we've always done it, which always involves Minkowski space, and we always kind of brush the underlying structure of space-time under the rug, but we can't really do that if you want to define quantum gravity, right? So ultimately, it's important and interesting to study quantum field theories on different surfaces so that we can understand how they work in all geometric settings, not just flat space. Flat space, it's easy. Flat space, we kind of have it under control. I mean, by and large, you can always just put it on the lattice, right? And then, done. Yeah. Anyway, that's all for today on Heisenberg modules. The next two videos are going to involve the action of the Vita-Soto algebra on Heisenberg modules, and I'm tempted to do them in reverse order, but I probably won't. So, hope you all are having a great winter. I will see you soon.